Okay, let's dive right in. If you're a final year BGE student, you already know the heavy pressure of the Capstone project. I mean, it's literally the culmination of everything you've learned so far. So today, we are going to completely demystify this process. We'll transform what is normally a really dense academic guide into your ultimate step-by-step blueprint for a flawless geomatics engineering project proposal. We're going to break down exactly what your department and your evaluators are actually looking for, so you can engineer a proposal that gets approved without a single hitch. To respect your analytical engineering mindset, we've kept our agenda super straightforward today. First, capstone path and research gap. Second, the 5-chapter blueprint. Third, literature and methodology. Fourth, outcomes, budget, and schedule. And finally, pro tips and pitfalls.
All right, Section 1, Capstone Path and Research Gap.
Now, before you even open up a word processor, you've got to figure out exactly what kind of project you're going to build or study. It's the foundational question every single final year student has to answer. Are you doing a geomatics project, or are you conducting geomatics research? They sound pretty similar, right? But academically speaking, they are judged on totally different criteria. Think of it like this. A geomatics project is totally execution-focused. You are taking known methods and applying them to solve a very specific practical problem. Basically, delivering a functional solution, like, say, developing a campus web GIS for facility management. On the flip side, geomatics research is inquiry-driven. This is where you explore the why and the how to discover brand new insights or test out hypotheses. A good example here would be evaluating machine learning algorithms for automated surface extraction from high-res satellite imagery. Generally, industry tends to prefer those execution projects, while academia really values the critical thinking of research. So just pick the path that aligns best with your actual career goals.
Now, if you do decide to go the research route, you can't just pick a topic at random out of thin air. There's a highly specific 5-step workflow for finding a worthy topic. First off, conduct a targeted literature review. Second, evaluate the technical limitations out there, like maybe traditional methods just lack the precision of low-cost GNSS. Third, go talk to stakeholders to find real practical industry needs. Fourth, do a reality check on feasibility to narrow your scope. Do you actually have access to hardware like total stations or LiDAR drones? And finally, validate the problem through clear documentation. You're basically building a bridge over the gap between academic theory and actual professional practice.
Which brings us to the most crucial point, defining your research gap. This essentially means pinpointing exactly what is missing in current academic knowledge. And hey, don't stress. As a final year student, nobody expects you to invent a brand new satellite sensor. A perfectly valid gap could just be taking an established technique and applying it to a geographic area that's never been studied before. Or integrating new tech, like a LiDAR workflow into a traditional mapping process just to see if it bumps up the accuracy. Moving right along to Section 2, the 5-chapter blueprint.
Now that you've nailed down your topic, we have to talk about the actual structural framework of your document. Because trust me, formatting and organization are just as important as your ideas here. Your proposal isn't just a giant essay. It's a highly constructed system built on 5 load-bearing chapters, plus your cover page, references, and appendices. Evaluators absolutely expect to see this exact narrative flow. If you try to get too creative and reinvent the wheel with your structure, you're just going to confuse the reader and lose easy points.
Speaking of not getting creative, even the cover page is strictly engineered. You absolutely must use an undistorted official university logo, A4 paper, Times New Roman font, and single spacing. You also need specific margins, typically 1 inch on the top, bottom, and right, and 1.25 inches on the left for the binding. I promise you, evaluators can spot a stretched out logo or a funky font size from across the room, and it immediately screams that you don't pay attention to details. When you get to Chapter 1, I want you to think of it literally like a funnel. You start super broad with the global context, like the big picture importance of tracking land surface temperature. Then you narrow that down to a specific deficiency, which becomes your problem statement. Maybe existing MODIS data is just too coarse for ward-level analysis. From there, you pinpoint your exact geomatics objectives, define the strict geographic and temporal scope of your work, and boom, you end with a precise research question. That funnel shape guides your evaluator perfectly, right into your project's rationale. That brings us to Section 3, Literature and Methodology. This is the core engine of your proposal. Chapters 2 and 3 are where you prove you understand the field and where most proposals either win or completely fail. For the literature review, please, whatever you do, avoid the massive amateur mistake of just listing paper summaries one by one. Saying author A did this and then author B did that is just a summary, not a review.
The winning standard here is grouping your sources by theme. You want to synthesize 10 to 20 peer-reviewed papers by analyzing them collectively. Group them by the sensor types they used or the algorithms they tested. You want to show the evaluator the actual trends and debates happening in the field.
Now, your methodology has to be bulletproof. And by bulletproof, I mean totally reproducible. You have to explicitly categorize every single dataset, tool, and parameter you're going to use. Using satellite data, don't just say Landsat. Specify the sensor, the spatial resolution, the specific bands, and the exact acquisition date. Flying a UAV, list the sensor model, ground sample distance, and the overlap percentage. You need to name every piece of software, ArcGIS Pro, Google Earth Engine, specific Python libraries, and every piece of hardware. Detail is everything, because a master evaluator should theoretically be able to replicate your entire project just by reading this one section. And for your study area map in Chapter 3, please don't just paste a quick screenshot from Google Earth. Getting this right means your map absolutely must have a north arrow, a scale bar, a legend, and a coordinate reference system label. Oh, and always throw in an inset locator map so someone who is totally unfamiliar with the region knows exactly where your study area actually is. All right, on to Section 4, Outcomes, Budget, and Schedule. Because this is an engineering proposal, you've got to prove your project is actually feasible within your time frame and resources. Evaluators are looking for a highly structured budget table. It needs to cover everything: fieldwork travel, accommodation, commercial credits for Google Earth Engine, software licenses, printing, the whole shebang. Always use realistic figures in your local currency. And crucially, always include a 10% contingency fund. Because if there's one thing we know about fieldwork, it's that the unexpected is definitely going to happen. This feeds perfectly into your Chapter 5 work schedule. This needs to be a Gantt-style work breakdown structure spanning your entire 6-month project lifecycle. But don't just list tasks out. Map them visually. Show where data collection and data processing overlap. And more importantly, factor in some risk assessment. What happens if a sensor completely fails or you get hit with 3 weeks of terrible weather? Your schedule needs built-in buffer time to prove you have a resilient, realistic plan. And wrapping things up with Section 5, Pro Tips and Pitfalls. Let's talk quality control, because the difference between a passing proposal and a top-tier one usually comes down to avoiding a few specific traps. First up, your objectives. A vague objective is your worst enemy here. Saying to study land cover changes is basically impossible to measure. Instead, you need smart objectives driven by heavy action verbs. To quantify seasonal land surface temperature change in impervious surface areas using Landsat 8. See the difference? That tells the evaluator exactly what you're doing, how you're doing it, and exactly what the deliverable will be at the end. Now watch out for these massive red flags that evaluators actively hunt for. An unreproducible methodology? Instant fail. Leaving out software versions, dropping random figures into the text without proper captions, or writing out this beautifully complex math equation but totally failing to define the variables directly below it? Those will cost you your grade in a heartbeat. And of course, double-check that your citations, whether they are IEEE or APA format, are completely flawless so you avoid even a hint of plagiarism. If you really want to blow your evaluators away, here are a few pro tips. Try using LaTeX through a platform like Overleaf for professional formatting. It handles equation numbering and citations like a dream. When it comes to visuals, remember the golden rule. One figure equals one message. Please don't cram 6 different concepts into a single map. Also, make sure every expected outcome in Chapter 4 is a direct match to a specific objective from Chapter 1. And here's a massive time saver: always write your abstract last. That way, it actually reflects what you wrote, not what you hoped to write 6 weeks ago. Well, there you have it. You now possess the complete architect's blueprint for a winning proposal. You know the exact structure, the pitfalls to avoid, and the intense precision your evaluators are demanding. So, the blueprint is literally in your hands. The only question now is, what complex geomatics challenge are you going to tackle to bridge the gap between academic theory and real-world impact? It's time to grab your data, map your timeline, and engineer something incredible.